Welcome to Part D of Unit 2 for our course on statistics. And we've been going through this googly-eyed sheep table regarding different types of distributions, where many of these distributions pertain to different types of error. And for each type of distribution, we've been looking at how we can describe that distribution by answering two questions. The first question is observations of what from what, and the second question is deviations around what. And so far we've looked at a standard deviation, and we've looked at distributions of estimation error, and we saw how the standard deviation of a distribution of estimation error is called the standard error of estimate. So we've looked at a standard deviation and a standard error of estimate. And for a standard deviation, we saw how the answer to that first question, observations of what from what, for a standard deviation, the answer is it's observations of cases from a sample. And the answer to the second question, deviations around what, with a standard deviation, we're looking at how far cases deviate around a sample mean. And then we looked at the standard error of estimate and distributions of estimation error. And the answer to that first question for estimation error was the same as we answered that question for a standard deviation. The question, observations of what from what, for estimation error, once again, it's observations of cases from a sample. But with estimation error, the answer to that second question was a little bit different. Deviations around what? Well, with estimation error, we're looking at deviations around a predicted value. Now, as we're going through this googly-eyed sheep table and these different types of distributions, one thing that you'll notice as we go along here is that some of these different distributions are going to be nested within each other. So the next type of distribution I want to look at is something called measurement error. And as we'll see in a moment, measurement error, to answer this first question, observations of what from what, measurement error will be observations of assessments from a single case. And so if we notice this nesting pattern, if measurement error is observations of assessments from a single case, then with standard deviations and estimation error, this was observations of cases nested within a sample. And with sampling error, well, that's the last thing we'll look at. We'll see that's going to be observations of samples nested within a population. So again, the next thing we're going to look at is measurement error, and that's going to be observations of assessments nested within a case. We've already looked at standard deviations and estimation error, which was observations of cases nested within a sample. And then the final thing we'll look at is sampling error, which is observations of samples nested within a population. So let's take a look at measurement error. Now, previously, when I talked about the standard deviation and distributions of estimation error, I printed the names of those distributions on a block of concrete to illustrate the fact that those were concrete distributions, things we could actually do a study and collect data and calculate. We could actually calculate a standard deviation, and we could actually calculate a standard error of estimate. Now we're going to move on to types of distributions that are more theoretical or hypothetical, things where we can't actually do a study and calculate these values, but we can talk about hypothetically what would happen if we could get these distributions. So I've printed the name of measurement error here at the top of the screen, is placed on top of this kind of futuristic science fiction looking picture to illustrate the fact that it's going to be a theoretical or hypothetical distribution. It's not something we could actually do a study and collect data and calculate a distribution of measurement error, but we can talk about hypothetically what would it look like if we could get this distribution. And a distribution of measurement error is going to pertain to the issue of reliability. So whenever we're talking about measurement error, we're going to be talking about reliability. And recall that reliability pertains to consistency in measurement. It's the extent to which we get the same numerical value every time we assess the same thing. So if I wanted to assess say, someone's level of depression, or how happy they were in an interpersonal relationship, or maybe how extroverted they were, if I assess that person on 2 occasions, if the person didn't change, to what extent do I get the same numerical value? Or if I use 2 different versions of an assessment instrument, does each instrument produce the same result? Now, one thing to keep in mind in just talking about reliability is that we're going to assume that there's an infinite pool of assessments that I could use anytime I want to assess something. So if I wanted to assess depression or relationship satisfaction, or say I wanted to assess how much a person likes green eggs and ham, I'm going to assume there's an infinite pool of assessments I could use to assess each of those things. And this infinite pool would include different items that I might use to assess that thing, different times that I might assess that thing, or different places I could conduct my assessment. For example, if I wanted to assess how much someone likes green eggs and ham, I could give them a question where I say, on a scale of 1 to 10, how much do you like green eggs and ham? Or maybe I give them a question where I say, ask them, how much do you agree with the following statement? When I think about green eggs and ham, I feel happy. So we could have an infinite number of different questionnaire items we might use to assess green eggs and ham. Or we can have other types of items. Maybe we do something where I give someone some green eggs and ham to eat, and I then observe the expression on their face to see how happy they look or how much they seem to enjoy it. Or I give them some samples and just see how much they eat. Or maybe I ask their friends to report how much they think the target person likes green eggs and ham. Those are all different items, different methods I could use to assess green eggs and ham. And I'm going to assume there's an infinite number of items I could use and different times. I could assess you in the morning. Maybe I assess you at 9 o'clock a.m. or maybe 9:15. Or I could assess you at 10:45, or maybe assess you at nighttime or in the afternoon or in the evening. Or I could assess you today or tomorrow or 5 weeks from now. So there's an infinite number of times that I could assess you. And there's an infinite number of places that I could assess you. I could assess you maybe on a room on campus, or I could assess you in your home. So I could assess you many different places. I could assess you in some location where maybe there's some kind of distractions going on, or maybe in another place it's really quiet. I could assess you in a noisy place or a quiet place. And so this fits with that Dr. Seuss book, Green Eggs and Ham. If we're wanting to assess how much someone likes green eggs and ham, we could kind of adapt this book to say, the question is, do we get the same numerical value if I assess you in a house? Or if I assess you with a mouse? Do I get the same numerical value if I assess you on a train or in the rain? Do I get the same numerical value if I assess you in a box or with a fox? So we assume there's this infinite pool of assessments that I could do to assess any one thing. So with that in mind, let's take a look at measurement error and see what it is. And here is the picture I have to illustrate a distribution of measurement error. And you will note that this picture looks quite a bit different from the picture I showed you to illustrate a standard deviation and the standard error of estimate. Here in this picture, I have just a single person, and I have pictures of the single person over and over and over and over again. So now, with the googly-eyed sheep table, the very first question to answer is the question, observations of what from what? And with measurement error, the answer to that question will be observations of multiple assessments from a single case. We're going to be looking at multiple assessments from a single case. And because we're observing a single case over and over again, that's why my picture just has the same face over and over again in the distribution there. And again, across the top, I've pasted the same person over and over again to say we're assessing the same person over and over and over again. And specifically, what we're going to assume here is that we have administered to this one individual, that we have given her the entire infinite pool pool of all the possible assessments that we could administer. So we're going to imagine what would happen if we gave this single person that entire infinite pool of possible assessments that we could use to measure something. So if we're trying to measure how much she likes green eggs and ham, we've given her the infinite pool of all the possible assessments we could use to measure how much she likes green eggs and ham. And just about anything we assess in psychology and neuroscience is going to have some degree of measurement error. There's almost nothing we can assess with perfect reliability. There may be a few things, but not much. That is, if we assess the same case and assume that case isn't changing, if we assess that same case, say using different items or different timings or different locations, we're likely to get a slightly different score each time we assess the case. So if we're assessing how much she likes green eggs and ham, if we assess her using different items or different locations or different timings, each time we assess her, we're likely to get a slightly different score on our scale. Sometimes she might score, maybe once we assess her, she gets way up here. And then maybe we assess her again and she gets a score down here. And we assess her again, she gets a score maybe kind of towards the middle, and maybe a score there, and then one here, and then one way out here, then one there, then one here, then one here, and here. So we keep assessing her over and over again. And each time we assess her, we're likely to get a slightly different score. And if we were, hypothetically, if we were to administer the entire infinite pool of all the possible assessments we could give this one single case, we would get this distribution. And the picture you're looking at here, this bell-shaped curve, is supposed to be the distribution of all the scores we got when we assessed this one single case over and over and over again an infinite number of times. So what are we looking at? Observations of what from what? We're looking at observations of different assessments, all taken from just one single case. The next question to address from our googly-eyed sheep table is the question, deviations around what? In other words, what is the midpoint of this distribution? Well, for a distribution of measurement error, the midpoint is something we will call a person's true score. A person's true score is the midpoint of a distribution of measurement error. In other words, if we're looking at repeated assessments of a single case with measurement error, we're looking at how far those assessments deviate from a person's true score. That is, we're going to say, hypothetically, what would happen if I were to assess the same person over and over and over again an infinite number of times, and if I were to administer that entire infinite pool of all possible assessments that I could administer to this one single person, and if I were to get all the scores from all those assessments and look at the distribution of all those scores, well, that distribution, that's what we're looking at right here. That's the distribution of measurement error. So this bell-shaped curve is supposed to be the distribution of measurement error. That's all the scores we got when I assessed the same person over and over again. So now if I were to take the average of all these scores in the distribution, the average would be that person's true score. It would be the midpoint of that distribution. We can also say it's the expected value for this distribution. That is, if I were to take just one assessment, in real life, that's what we typically do. We don't assess a person an infinite number of times. So if I were to assess a person on just one occasion, here I'll circle one of these pictures at the top here to say this is just one single assessment. So if I just assess this person on one time, what is my best guess for what that person's score is likely to be? Well, hypothetically, if I knew that person's true score, the true score would be my best guess for what that person's observed score is likely to be. Now, of course, in real life, I don't know someone's true score, and if I did know someone's true score, I wouldn't need to conduct an assessment. But hypothetically, we can ask the question that if I didn't know the score for this single assessment, what is my best guess for what I would get on this particular assessment occasion? My best guess is that I would get that person's true score. So we can say a true score is an expected value. It's the score I would expect to get for a single person on a particular assessment occasion. Another way I could say the same thing is I could say that a true score is the score we would get if I could assess someone with perfect reliability. If I had a scale, if I had an instrument that had perfect reliability, then that would give me the person's true score. Because if an instrument had perfect reliability, then all the scores, every time I assess the same person, I would get the exact same value. If it had perfect reliability, I'd get the same value every time I assessed the person. So all the scores would be just stacked on top of each other, right on top of a person's true score. So we could say that a true score is a score we would get if I were to assess a person with perfect reliability. One thing to note here is that the term true score can be a little bit misleading because we're talking about reliability here. We're not talking about validity. So I can talk about someone having a true score, but that has nothing to do with whether or not my instrument has validity. Recall the difference between reliability and validity. So reliability has to do with consistency in measurement. To what extent do you get the same value each time you assess the same thing? That's reliability. Validity has to do with whether or not you assess the thing you claim to be assessing. Is your measure assessing the thing you claim to be measuring? So, for example, what if I was wanting to assess, say, statistical knowledge? Maybe I was going to give a final exam in one of my classes, and I wanted to assess statistical knowledge in students. And maybe I had a method for assessing statistical knowledge that went like this. I gave people different flavors of jelly beans, and I asked them to sniff the jelly beans and recognize what flavors those jelly beans were. And people that could better recognize the flavor of jelly beans got higher scores, and people that didn't sniff and recognize flavors so well got lower scores. And I could use that method to measure statistical knowledge. Now, that would be a completely invalid measure. That measure would have terrible validity. But I could still ask the question, how reliable is my scale? How much do people's scores fluctuate from one assessment to the next? And every person would have a true score on my jelly bean sniffing scale. I could say this is your true score for my statistics test. Now my test might have terrible validity, but you would still have a true score. That is, if I were to administer my jelly bean sniffing test an infinite number of times in different places and maybe with different flavors of jelly beans, with different types of jelly bean sniffing items. If I were to administer the entire infinite pool of all the possible jelly bean sniffing tests that I could administer, and if I were to administer that entire infinite pool to a single person and then take the average of all those assessments, that would be the person's true score on my test. And if I am calling that test my statistics knowledge test, that would be your true score for statistics knowledge. Now, it's misleading because to say you have a true score for statistics knowledge doesn't mean anything about whether that score is actually valid. In this example, that score would have zero validity, but you would still have a true score. So keep in mind the fact that when I'm talking about a true score, I mean it's the score I would get if my test had perfect reliability. It's a score I would get if I were to assess you an infinite number of times and then take the average across all my assessments. And asking the question about what is the perfectly reliable score I would get is a different question from whether your score is valid or not. So a true score has nothing to do with validity. You can have a true score on a test that has zero validity. The true score is simply the midpoint of the distribution of measurement error. It's a score we'd get if we assessed you with perfect reliability. It's a score we would get if we assessed you an infinite number of times and took the average of all those infinite assessments. So in conclusion, when we're talking about measurement error, the first question, observations of what from what, we're looking at observations of assessments from a single case. Deviations around what, we're looking at deviations around a true score. how far these multiple assessments on a single case deviate above or below a person's true score. And like all distributions, a distribution of measurement error will have a standard deviation. And we're going to call the standard deviation of a distribution of measurement error, we're going to call that the standard error of measure. So the standard error of measure is the standard deviation of a distribution of measurement error. And we'll abbreviate that with SD, which stands for standard deviation, with the subscript MEAS, which stands for measurement error. Now, it's a little bit confusing because we have several terms that I'm going to use throughout this unit that will all begin with the words standard error of. So we've already talked about the standard error of estimate, and now we're talking about the standard error of measure. And actually later we're going to talk about something I will call the standard error of different statistics. And these are all going to be standard deviations of different types of error distributions, but they're standard deviations of very different distributions, and they mean very different things. So we have several terms that all begin with the words standard error of, and it's important to keep track of the differences between these different distributions. The standard error of measure is the standard deviation of a distribution of measurement error. So that's if we assess the same person over and over and over again an infinite number of times and get all those scores when we give the infinite pool of possible assessments to the single person, and then look at how far on average does each assessment typically deviate from that person's true score. If I assess that person on one occasion, how much does that one assessment deviate from her true score? And if I assess her over and over and over again an infinite number of times, on average, how far does each assessment typically deviate from that person's true score? And that is the standard deviation of this distribution of measurement error. That's what the standard error of measure tells us, how far on average a person's observed assessment typically deviates from that person's true score. So here I have this double-headed arrow down here with the word arrow in it, that blue double-headed arrow, and that's the size of the standard deviation of this distribution. And in this case, we're looking at measurement error, so that's the standard deviation of measurement error, the standard error of measure, and it's telling me how far this person's assessments typically deviate from that person's true score. If I say the standard error of measure is 3, then on average, that person's assessments will deviate 3 units from that person's true score. The standard error of measure tells me how much each assessment typically deviates from the person's true score. And that's the standard error of measure. And as with the other distributions that we've been looking at, I have linear equations to give you that we can use to describe a distribution of measurement error and to describe the standard error of measure. And these linear equations are listed in the lower left-hand corner of the screen down here. So let's take a look at these equations and see what we have. Now, one thing to note is that I'm going to go back to using the letter x on the left-hand side of my equation because I'm only looking at one variable, which I'll call variable x, and I don't have any predictor variables. So what do we have? We have an x with a hat on top, so the predicted score on variable x, and I'm going to have subscripts AI to indicate this is the predicted score on assessment occasion A for individual I. So this is going back to that googly-eyed sheep table, observations of what from what. With measurement error, we're looking at observations of different assessment occasions nested within a single case or a single individual. So we're no longer looking at cases nested within a sample or individuals nested within a sample. Now we're looking at different assessment occasions nested within a single individual. So I'm going to say the predicted score on variable x for assessment occasion A of individual I, that is x hat subscript AI, is equal to the true score for individual I. In other words, I have these the same person over and over again at the top here, so I'll circle just one of these. say this, I'm circling just one assessment occasion of this individual person. And I can say, what is my predicted score, x hat? What do I predict I'm going to get for that person on that single assessment occasion? That's x hat for this particular assessment occasion of this particular individual. And I'm going to say the predicted score for that person, x hat, for assessment occasion A of individual I is equal to the true score of individual I. And that's if I were to assess this person an infinite number of times and get this distribution over here, look at our distribution of measurement error, the midpoint of that distribution, that's that person's true score, is the average of all those assessments. So the true score for individual I is what we would predict. So that's what that equation is saying. It's the predicted score on variable x for assessment occasion A of individual I is equal to the true score for individual I. Or we could take away the hat and write the equation at the bottom way, and down at the bottom we have the actual score on variable x. The actual score we get on assessment occasion A for individual I is equal to the true score for individual I plus however much error we made on assessment occasion A for individual I. That's how much error we made on that particular assessment occasion. So if I'll circle the one, if I do this one assessment up here and I get this one score, maybe this score is up here. So I can say how much does that assessment deviate, or maybe I assess her, maybe her score is down here. How much does that assessment occasion deviate from her true score? That's the amount of error that I get. The error is how far as an assessment occasion, a score from an assessment occasion deviates from that person's true score. And with all these equations, we can then say, well, if I were to assess her an infinite number of times and get all these errors, if I get all the errors from all these infinite assessments, and then say, what's the average absolute value of all those errors? On average, how much error am I making each time I assess this person over and over and over again an infinite number of times? And we could say, what is the average deviation of that? Well, that is the standard error of measure. That's what the standard deviation tells us. The standard deviation of this distribution tells us how far each assessment occasion, scores from assessment occasions, typically deviate from a person's true score. That's the amount of error that we make. The amount of error is how far the score from the assessment occasion deviates from the true score, and the average amount of that absolute value of error, the average amount of error that we make, is the standard deviation of that distribution. So the standard deviation of our distribution, which we call the standard error of measure, gives us the average deviation of the absolute values of these EAIs, the error for assessment occasion A of individual I. And that's what the standard error of measure gives us. And so those are the linear equations we can use to describe measurement error. Now, up to this point, my discussion of measurement error has been rather abstract. I've been talking about hypothetical situations. I said that the standard error of measure is what we would get if I were to assess a person an infinite number of times and administer the entire infinite pool of all possible assessments that we could administer, and to get all the scores from those assessments and calculate the standard deviation from all those scores. That would be the standard error of measure, and it would tell us how far on average scores from each assessment occasion typically deviate from that person's true score. But we can't possibly assess a person an infinite number of times, and we can't possibly know a person's true score. So this is all very abstract and hypothetical. But now I'd like to move us in a more concrete direction and talk about something we actually can do. Because we can take this concept of measurement error and use it to calculate an estimate of reliability for a particular assessment instrument. So let's look at how we can use measurement error to calculate reliability. And to do that, I first need to define three terms. I need to define total variance and measurement error variance and true variance. So what are these three things? So for example, imagine that I give a test, maybe I give a final exam in one of my statistics classes. And assume that this is a valid test, not that I'm not doing that silly jelly bean sniffing test I talked about a moment ago. So assume I have a valid measure of statistical knowledge, and I give a final exam in one of my statistics classes. And when I do that, I will get a distribution of scores from all the students in my class. And let's assume that this distribution in the upper left-hand corner of the screen is a distribution of scores that I get from all those students. And that distribution will have a variance and a standard deviation. And technically, when we're dealing with reliability theory, we're going to be dealing with variances, which are squared standard deviations and not standard deviations themselves. But that's not actually that important for this discussion. Just know that this distribution will have a variance, and the key thing to note is that scores will be spread out. There'll be a range of scores. Some students will have higher scores, some students will have lower scores, some students will be in the middle. Scores will be spread out to some degree, and that will be the variance that I get. Now, with reliability theory, we're going to look at this variance and ask a question, a very simple question. Why do we have variance? Why are scores spread out? Why didn't everyone get the exact same score? If some students did better and some students did worse, why is that? And if we're thinking about reliability theory, we're going to answer that question by saying there's two reasons why there's variance. There's two reasons why students didn't all get the same score. And those two reasons are this: because total variance will be comprised of two things. One thing that will make scores go up and down is that there could be differences between students in their true scores. That is, the scores we would get if I had a perfectly reliable measure of statistics. If my instrument was perfectly reliable, some students might have better statistical knowledge and they might perform higher on my test, and other students might have less statistical knowledge and they might perform lower, and differences between students in their true scores would produce total variance. So, and I have this circled down here. So true variance is the variance I get between students that's due to differences between students in their true scores. But that's not the only reason that students will differ from each other. Another reason that students will differ from each other is due to measurement error variance. So measurement error variance is the differences I get between students that's not due to differences in true scores, that's due simply to measurement error. Because we know that with measurement error, if I assess a single person over and over again, each time I assess that person, I'm likely to get a slightly different score. So given that, if I had students in a class and every single student had the exact same true score, say every student had the exact same level of statistical knowledge, and every student had the exact same true score on my test, I would still expect to get differences between students. I would expect to get differences because each time I assess a student, part of what I'm going to get is measurement error. Those fluctuations, those random fluctuations that will happen from one assessment to the next, that's simply due to measurement error, and that's not due to differences between students and their true score. So with reliability theory, we're going to say this. We're going to say that total variance, that is differences between students on that test. Why are students different from each other? Why didn't everyone get the same score? Why is there variance between students in their scores on my test? The answer is there's two reasons, two different causes for that variance. One cause is there's differences between students in their true scores. That's going to be, we're going to call that true score variance. And the other reason is there's going to be differences between students simply caused by measurement error because we can't assess students with perfect reliability. And differences that are caused by measurement error we're going to call measurement error variance. And we're going to say that those two things added together, we're going to say that, for example, if I take total variance and I subtract out from that total variance the amount of differences that's caused by measurement error, that's going to equal true score variance. Or I could say it this way: if I take true score variance plus measurement error variance equals total variance, or total variance minus true score error variance equals measurement error variance, or the way it's depicted on the screen, I'm going to say that total variance minus measurement error variance equals true score variance. So if I calculate what's the total variance on a test that I gave in a class, and then if I could estimate, well, how much of that variance do I think is caused by measurement error? How much measurement error do I have on this test, and how much do I think that might be causing differences between students in their scores? And so how much of this total variance is actually stuff that's simply due to measurement error variance? And if I were to subtract out measurement error variance from total variance, that would give me something called true score variance or true variance. So that's what I mean by total variance, measurement error variance, and true variance. And let's take this a little further and see how we can apply this to the idea of reliability. So now at this point, if you understand the terms for total variance and true variance and measurement error variance, we can use these terms to define what reliability is. And then once we've defined reliability, I can talk about a way that we can actually estimate the reliability for a particular assessment instrument. So what is reliability? Well, reliability is simply this. If I take the true variance on an assessment instrument and divide that by the total variance, I would get the reliability. So for example, if I administer a statistics test to students in one of my classes and calculate the total variance on that test, and if I had a way to estimate the true variance on that test, I could take true variance divided by total variance, and that would give me the reliability of my test. And note that if I take true variance divided by total, that essentially gives me the percent of variance that is true. So if I take true variance divided by total variance, that gives me the percent of my total variance that is true variance. And so we define reliability as the percent of variance that is true. That is, it's what we get if we take true variance divided by total variance. Now, as it turns out, we don't actually need to administer that entire infinite pool of all possible items in order to get an estimate of reliability or measurement error. Because if I have just two assessments that are both drawn from that infinite pool of all possible assessments I could give, I could calculate the correlation between those two assessments. And if I do that, we could show that the correlation between those two assessments is actually a good estimate of reliability. So on the screen here, I have R test 1, test 2. And that's the correlation between test 1 and test 2. So if I have R subscript test 1, test 2, it's the correlation between test 1 and test 2. And test 1, that simply means that's one assessment that's drawn from that pool of all the possible assessments that I could give. And test 2, that's a different assessment that's drawn from that pool of all possible assessments that I could give. And so what it's showing on the screen here is that the correlation between test 1 and test 2 is approximately equal to, it's a good estimate of, true variance divided by total variance. So true variance divided by total variance is approximately equal to R test 1, test 2, a correlation between two assessments that are both drawn from that pool of all possible assessments that I could give. And true variance divided by total variance gives me the percent of variance that is true. And the percent of variance that is true is reliability. So therefore, the correlation between two tests is an estimate of reliability. And we could actually look at some formulas and do a proof to show that this is true. We could do a mathematical proof to show that this is actually true, that a correlation between two tests is a good estimate of reliability. It's approximately equal to reliability. And if you take my measurement course, we will take a look at why this is true, and we will look at some of those proofs that show this is actually true. For now, I'm going to ask you just to trust me that we could show this if we wanted to, that we could prove that the correlation between two tests is a good estimate of reliability. So what this means is, for example, if I had my statistics course and I gave a final exam in my statistics course, we could estimate the reliability for that final exam. So for example, say I have a class of, say I have 50 students, and every student takes the final exam, and then say they come and they turn in their final exam, and I say, wait a minute, before you go, I want you to take another final exam. So you just took a first version of that final exam. I have a different final exam that has different questions on it, and I want you to take that one too. And so if I had a class of 50 students, and every one of those students took 2 different versions of the final exam, that is, I'd have scores on test 1 and test 2, I could then calculate the correlation between those 2 tests, and that correlation would be an estimate of reliability. So if I calculated that correlation, and the correlation was 0.8, well, that would be the reliability, that would be the estimate of reliability for that test. That would mean that for this final exam, 80% of the variance was true variance, and 20% of the variance was due to measurement error. That the reason why students got different scores, 80% of the reason was due to actual true differences between the students, and 20% of those differences were simply due to measurement error on the test. So the correlation between 2 tests that are both drawn from that pool of all the possible tests we could give, the correlation between those 2 tests is an estimate of reliability. It's an estimate of the percent of variance that is true. So I can get an estimate of reliability if I calculate the correlation between 2 assessments, or between 2 tests, if they're both measuring the same thing. That is, if they're both drawn from the same infinite pool of all possible assessments that I could give. So what are all the ways that I could do this to estimate reliability? One thing I could do is something called alternate forms reliability. And alternate forms reliability is actually what I was describing on the previous slide, where I talked about having 2 different versions of a final exam. So anytime I have 2 different versions of an assessment instrument, and I administer both versions to a sample of people, if I calculate the correlation between those 2 versions, that gives me alternate forms reliability. So, for example, say I was assessing the personality trait of extroversion, and maybe I had a questionnaire that had 10 items on it with questions asking about traits of extroversion, and people would respond to those 10 questions, and then I would add their responses together to get a total score on my questionnaire assessing extroversion. Now, if I had 2 different versions of that questionnaire, maybe version 1 included 1 set of questions asking about traits of extroversion, and the second version, the alternate version, had a different set of 10 questions asking about extroversion. And if I had a sample of people and I asked them to complete both the first version and the second version, then I could calculate the correlation between scores on those 2 different versions of my extroversion questionnaire, and that correlation between my 2 versions, or between my 2 forms, is called alternate forms reliability. Another thing I could do is something called test-retest reliability. And with test-retest reliability, I'm going to give this same assessment instrument to people on 2 different occasions. And the spacing of these 2 occasions could be anything. It could be 2 occasions that are maybe 1 day apart from each other, or maybe they're separated by 1 week apart, or maybe it's 1 month, or maybe it's several months. But anytime I give the exact same assessment instrument to people on 2 different occasions and calculate the correlation between scores on those 2 occasions, that would give me test-retest reliability. So maybe I have a sample of people and I give them my 10-item extroversion questionnaire and I get their scores on extroversion. I just give them 1 version in this example. So I give them my first version of my extroversion questionnaire and they complete that. And then I ask them to come back maybe 2 weeks later and complete that exact same questionnaire a second time 2 weeks later. And then I get the correlation between those 2 assessments, that will give me test-retest reliability. Now, at this point you may be thinking, this sounds like a lot of work. Is there a way we could make this easier? For example, if I want to get the reliability for my final exam in my statistics class, the options I've given you so far, we could do alternate form, where everyone takes the final exam and then I give them an alternate form and they do it a second time and take that a second version of my final exam. Well, that would sound like a lot of work. And I imagine if students have just completed a final exam in my class and I say, now let's take another one, they might not be very happy about that. Or if I say, okay, you finished the final exam today, I want everyone to come back in 1 week and to take the same exam all over again. And we could do test-retest reliability, where everyone takes the final exam on one day and then they come back 1 week later and test it again. And we could do test-retest reliability. But these things sound like an awful lot of work. So what about this? Is there some way that maybe I could just give one assessment and pretend like it's two? Could we do that? Could I just give you one final exam and pretend like it's two? Could I just give you one questionnaire measuring extroversion and pretend like it's two? And the answer is, why, yes, we can do that. And we could do something called split half reliability. So split half reliability is where I give just a single assessment instrument, but I pretend like it's two. I divide it in half some random way. So if I have, say, a bunch of items, I might say all the odd items or all the odd questions on this questionnaire will be called test 1. And all the even items or all the even questions will be test 2. So I take a single test and I randomly divide it into 2 parts. And I call one part test 1 and the other part test 2, or assessment 1 and assessment 2, or questionnaire 1 and questionnaire 2. And then I get the correlation between those 2 halves. Now, one thing that's going to happen here is that when I divide my test into 2 halves, each half has only half the number of items as the full test. So if I have a questionnaire with 10 items and I divide it into 2 halves, I have 2 questionnaires with 5 items each. And a questionnaire with only 5 items will be by definition less reliable than a questionnaire with 10 items. So when we do split half reliability, we'll use some formulas, and I'm not going to get into those formulas here, but just note that we will need to use some formulas to adjust for the fact that we're shortening the length of our test. So what we do with split half reliability is we divide our test in half and we calculate the correlation between our 2 halves, and then we make a little adjustment to account for the fact that our 2 halves are shorter tests than the full version of our test, and the shorter tests will have slightly lower reliability than the full version. But essentially we're just getting the correlation between 2 halves of our test, and we just do some kind of random way of splitting our test in half and getting the correlation between those 2 halves. Now, I would actually never do a split half reliability and report it in a paper, because there's actually, if I'm going to try to use a single test and pretend like it's 2, there's a better way to do it, and that's something called Cronbach alpha. And Cronbach alpha might be the most widely used method for calculating reliability. If you look at journal articles, every time a research study reports the results in a journal article, they should report the measures. They should describe what the measures are that are being used in that study. And for every measure that's reported, the researcher should report the reliability of that measure. And every time that if you look at reliabilities that are reported, the most common reliability you're going to see reported in the literature is Cronbach alpha. So if you look at journal articles and researchers reporting results from research studies, you should find lots of examples of researchers reporting Cronbach alpha. And Cronbach alpha is one way of measuring reliability. It's similar to a split half reliability in that it's going to estimate the reliability, how much 2 different tests correlate with each other, using results from just a single test or in a single assessment. Technically, what Cronbach alpha does is it actually takes, say I have a questionnaire measuring extroversion that has 10 items on it. Cronbach alpha is a set of formulas that will look at the correlations between the items on my test. So if I have 10 items on my test, Cronbach alpha will use the correlations between the items on my test to estimate how much my test would likely correlate with an alternate form. So again, the Cronbach alpha looks at the correlations between the items on a single assessment or a single test to estimate how much that assessment or how much that test would correlate with an alternate assessment or an alternate test that's drawn from that same pool of all the infinite assessments that could be given. Now, as it turns out, a Cronbach alpha is also equal to what you would get if you were to calculate a split half reliability and then to split your test in a different way and calculate split half reliability, and then split your test in a different way and calculate split half, and split your test in all the different ways you possibly could split it, and then calculate the average of all your split half reliabilities, you would actually get Cronbach alpha. And so split half reliability is really not as good as a Cronbach alpha. Maybe many years ago, when people sometimes calculated things by hand, it might make sense to do a split half reliability because it might be a little easier to calculate that by hand. But today, when we can use computers to calculate things, I would never use a split half reliability because Cronbach alpha is a better estimate of reliability. So the most common estimate of reliability you will see out there in research is a Cronbach alpha. And again, a Cronbach alpha is a method that looks at the correlations between the items on an assessment or between the items on a test. And based on the correlations between the items on a test, it estimates how much that assessment or how much that test would correlate with an alternate form that's drawn from the same pool of all the infinite assessments that could be given. That is, it estimates how much that test would likely correlate with another measure of the same thing, and that is an estimate of reliability. So if you use Cronbach alpha to calculate an estimate of reliability, or if you use any of those other methods to calculate reliability, how do you decide what levels of reliability are good reliability? What are typical levels of reliability that you might find, say, in research practice where you're assessing participants in a research study, or in clinical practice where you're assessing clients, or in an educational setting where a teacher is assessing students? What are typical levels of reliability, and what are good levels of reliability? So for this class, we're going to use these arbitrary cutoffs that I have here, and we'll say that if reliability is less than 0.7, we're going to call that problematic or poor reliability, and 0.7 or higher, we're going to call that adequate reliability, and if your reliability is 0.8 or higher, we're going to call that good reliability. And if you look at reliabilities as they're reported in research or educational settings, you'll find a lot of examples of reliabilities that fall in this range. It can take a little bit of work to get a reliability of 0.8 or higher, but we'll call that good reliability. And sometimes there are some assessment instruments that have gone through extensive development, and sometimes you can get reliability even up to the 0.9 range or even slightly higher. That's kind of rare. So common reliabilities are in the 0.7, 0.8 range in terms of what you'll usually see in real life situations. So for example, if I give a final exam on one of my classes and I calculate Cronbach alpha for my final exam, and the Cronbach alpha is 0.8, I will say that exam has good reliability. And that's pretty good reliability. A lot of times if I have tests, I might actually have reliability lower than that. So 0.8 actually is somewhat difficult to achieve reliability that good, especially for an educational test. It's hard to get reliability of 0.8 or higher. And so if I get reliability that good, I'll say, oh, that looks pretty good. That's good reliability. But note what that means. A reliability of 0.8 means that 80% of student scores are due to true score differences between students, and 20% of their scores are due to measurement error. So how would you feel about that if you take a test in a class and you discover that the reliability is 0.8, meaning 20% of your score on this test was due to random measurement error. Would that make you feel good about the test? You might feel a little bit upset about that, but the truth is that's actually good reliability. It's actually somewhat difficult in real life. It's difficult to get reliability much higher than that, especially on an educational test. You have probably taken many tests in your life that have reliabilities that are much lower than 0.8. So this is another place where this course can help give us perspective on real life situations. A lot of times people take tests and maybe have a vision that the test has near perfect reliability. But in real life, it's hard to get a test that has very high reliability. And 0.8, if you have a test where 80% of your variance is due to true score differences between people, and only 20% of your variance is due to measurement error, that's typically considered pretty good reliability, at least compared to what we can get in real life situations. So, I've been talking about distributions of measurement error. And in talking about measurement error, I've talked about the standard error of measure. That's the standard deviation of a distribution of measurement error. That tells us how far on average different assessments of the same person typically deviate from that person's true score. And we've been talking about reliability, and reliability is the percent of variance that is true. And we talked about how we can estimate reliability. For example, we can calculate Cronbach's alpha. And reliability is estimated essentially by getting the correlation between two assessments of the same thing. That is, two assessments that are both drawn from the same pool of all possible assessments that could be administered. So we talked about a way that we can estimate reliability. What if I wanted to know what the standard error of measure was? For example, say I had my questionnaire measuring levels of extroversion, and I wanted to know what the standard error of measure was for my questionnaire. Maybe I calculated a Cronbach's alpha, and maybe my Cronbach's alpha was, say, 0.82, so I had good reliability. But what if I also wanted to know the standard error of measure for my questionnaire? That is, I wanted to know when people take my questionnaire, on average, how far does each assessment typically deviate from each person's true score? How much mistake is this questionnaire likely to make? That is, how close are people's actual scores on my questionnaire likely to come to people's true scores? What's the typical deviation? How far do observed scores typically deviate from true scores on my questionnaire? That's the answer that's answered. That's the question that's answered by the standard error of measure. Because the standard error of measure tells me how far each assessment from a person typically deviates from that person's true score. So if I have a measure of extroversion, I might want to know what the standard error of measure is for my questionnaire. So if I can estimate reliability, can I also estimate the standard error of measure? And the answer is yes, we can estimate that as well. And as it turns out, there's a direct relationship between the standard error of measure and reliability. On this slide, I'm going to show you how these two things are directly related. And then on the next slide, I'm going to give you a formula that you can use to calculate the standard error of measure. Essentially, on this page, I'm going to give you formulas that only work with z-scores. And I'm just giving you these formulas to set you up for the next formula, which is the full formula that tells you how you can calculate the standard error of measure in any situation. But it's easier if we start with saying, well, what if we have z-scores? For example, what if I have my questionnaire that's measuring extroversion, and I turn everyone's score into a z-score, and I want to get the standard error of measure in z-score units. That is, how many z-scores do people's observed scores typically deviate from their true scores? So if I want to get the standard error of measure in z-score units, I can estimate that if I have a measure of reliability. So for example, if I've calculated Cronbach's alpha, and Cronbach's alpha gives me an estimate of reliability, I can take that value I got from Cronbach's alpha and plug it into a formula to estimate the standard error of measure. And the formula gets really simple if I want to deal with squared values. So if I want to say what is the squared standard error of measure, that turns out to be equal to simply 1 minus reliability. So 1 minus reliability. So essentially, the squared standard error of measure is simply the opposite of reliability. It's simply 1 minus reliability, and that gives you your squared standard error of measure in z-score units only. Now, if I want to get rid of that square, if I want to unsquare it and get just the regular unsquared standard error of measure, I then need to take the square root of this. So the standard error of measure, and again, this is only true, this formula right here only works if I'm dealing with z-scores. So if I have my measure of extroversion and everyone's score has been turned into a z-score, it's been standardized, then this bottom formula works. The standard error of measure would be equal to simply the square root of 1 minus reliability. So if I'm dealing with z-scores, standard error of measure is simply the square root of 1 minus reliability. And here is the full formula for the standard error of measure. This is the formula that you need to know, and this is one that will work on any kind of scale, regardless of whether it's a z-score scale or not. So what we're going to do here is we're going to take the square root of 1 minus reliability, that's that same thing we saw on the previous slide, and we're going to multiply that by the standard deviation of our scale. Note, if I was using a z-score always has a standard deviation of 1, and so this standard deviation would simply be 1 if I had a z-score scale, and then that would drop out of the equation, and it would simplify to square root of 1 minus reliability, which is what we saw on the previous slide. You can think of it this way. When I calculate a z-score, when I standardize a variable, I take a centered score and divide it by a standard deviation. So we divide things by a standard deviation to standardize. If I multiply something by a standard deviation, I'm going to unstandardize it. So essentially what we're doing here is we're calculating a standardized standard error of measure, and then we're multiplying it by a standard deviation to unstandardize it into a raw score a scale that's measured in raw score units. So for example, if I had a measure of extroversion, and say my measure of extroversion, maybe it had a standard deviation of, say it was equal to 5, and say I calculated Cronbach's alpha, and say Cronbach's alpha was, I don't know, equal to 0.8. And so then I could plug that into my equation here. I could say 1 minus 0.8, take the square root, multiply it by my standard deviation, and that would be 5. So 5 times the square root of 1 minus 0.8. I think that's going to give me 2.23 if I calculated that right. Oops, 2.23. So if my standard error of measure, if I calculate that to be 2.23, for example, say I calculate my standard error of measure and it's 2.23, what that means is if I have my scale measuring extroversion, each time someone completes my scale, on average, the score that I observe for any one person is typically going to be about 2.23 units away from that person's true score. Every time someone completes my measure of extroversion, if the standard error of measure is 2.23, that means every time someone completes my questionnaire, on average, people's observed scores are going to deviate about 2.23 units away from their true scores. On average, that's how much measurement error I'm getting every time I assess someone. So that's how you can calculate the standard error of measure using your estimate of reliability. And here is a song about the standard error of measure. And this song essentially defines what the standard error of measure is. So we have, if you test me many times, my scores will change and stray from true. And if you go back to that googly-eyed sheep table and the two questions we addressed regarding the googly-eyed sheep table, the first question was observations of what from what? And for measurement error, the answer was observations of different assessments from a single case. So here we have, if you test me, a single case, many times. That's describing doing multiple assessments on a single case. Or technically what we're doing is if we administered the entire infinite pool of all possible assessments to a single case. Or we can simplify it to if you test me many times. And then the second part of the googly-eyed sheep table, the second question was deviations around what? And for measurement error, we're looking at deviations around a true score. So how far do scores stray from true? So we're saying if we assess a single case multiple times, each score will deviate some amount from a true score, or my scores will change and stray from true across each of these assessments. And then the standard error of measure tells us how far on average each of these observed scores, on average, how far they typically deviate from someone's true score. So this is the song about the standard error of measure. And again, I encourage you to listen to it and then try to sing with it, and then see if you could sing along with the song without looking at the words. So here is the song for the standard error of measure. And that is everything for part D of Unit 2.